Please let me introduce our first speaker, Dr. Erika Rebrosova. Erika is the Global Technology Manager for Electronic Materials at Sun Chemical. She is responsible for leading new product development and technology support for application in printed electronics, biosensors, printed circuit boards, and photovoltaics. Erika has been working in coding technologies for electronics application for over 15 years. She co-authors multiple technical publications in the field and actively participates at various standard development committees. She received her PhD degrees at Western Michigan University, where she worked closely with industrial partners as a research faculty member of the Center for Advancement of Printed Electronics. So please welcome Erika. She's going to talk about the high-resolution screen printing for flexible hybrid electronics applications.
Thank you, Martin. Hi, everyone. Good to be here. And thanks to the CPS organizers for the opportunity to speak to you today. My topic is high-resolution screen printing for flexible hybrid electronics applications. Next, please. Okay, so first off, let me start by a brief introduction to Sun Chemical. You can see some basic statistics about the company. We have a very long history of ink manufacturing, more than 200 years in the business, which makes us the leading manufacturer of inks, coatings, pigments, and advanced materials for a variety of markets. Next slide, please. The core business of Sun Chemical revolves a lot around color, but we offer material solutions to market outside of the traditional graphic arts, and electronics is actually a big part of that. For example, our image cure solder mask products, whether it's liquid photoimageable or direct imaging products, are well known in PCB manufacturing. We supply materials for printed electronics, FHE, biosensors. We also sell PSA tapes and foams for assembly. And finally, our etch and plating resist for solar market. So that's in a nutshell on the product categories and on Sun Chemical. Let's get to the main topic of today. So first, I'd like to talk about the main drivers for high-resolution functional printing. You may be familiar with the term HDI or high-density interconnects, or in our case, I actually added a P there. I call it HDPI as high-density printed interconnects. And this is in line with trends in traditional copper circuits, though the target resolution for copper circuits is a little bit higher than what we are aiming for today in printed electronics or in silver circuits. With HDPI, we could design more complex circuits with higher count, and smaller components or connectors can be used. So it would also allow smaller size parts that can fit in tighter spaces of the devices or electronic panels. The second driver is transparency, and this is really related to fine metal mesh printing, which seems to be more reliable than some of the other alternative ITO alternatives or transparent conductor alternatives. Now, transparent metal mesh, the metal lines required to be very fine in order to be transparent. These would be useful for backlighting applications, for transparent cap switches, for transparent antennas, heaters for lenses, de-icers, and things like that in automotive applications. For example, in RF, in radio frequency applications, there are small features, intricate and complex designs with very fine lines and gaps are required, and very sharp corners are needed. So we all know about 5G or even the 6G technologies coming. And finally, we look into potentially lower costs, right? So printing narrower lines allows for a better cost efficiency, as there is less silver ink needed or less precious metal. And we already know that using additive processing is cheaper and better for environment. And by developing higher resolution screen printing and materials for high resolution screen printing, we can actually increase competitiveness and expand applications for screen printed circuits versus the subtractive manufactured copper circuits. So I think that's really the key takeaway from what I was trying to cover on this slide. Next slide, please. Pushing limits never comes easy in any area, right? And there are some challenges that needs to be overcome in order to really make high resolution silver circuits a reality. I put together this table that lists some of the main challenges, and in respect of time, I won't go through all of these, but to mention some of the few important ones. For example, for HDPI applications, high density interconnects, improvements in assembly technologies may be needed. Now, ECAs are often used in printed electronics, but for more complex and smaller circuits, we may need to look into the low temperature solder paste, which would be more suitable for better alignment and reliability of the joints. Press room cleanliness becomes more important, as small specks of dust and fibers can really affect production yield. So this is something that the print shop need to get on board with, right? They need to start looking at the cleanliness, maybe introducing some a certain level of clean room environment into their process, and the handling and the procedures. And from the materials perspective, as the traces get smaller, we really need to maximize conductivity of inks to be able to deliver sufficient current carrying capacity for a given application. So there is definitely an opportunity for innovation, not only in materials, but also in the manufacturing processes itself. All right, next slide, please. So let's look at some actual numbers and targets for trace dimensions. Today, production scale silver circuits are not much smaller than 125 to 150 micron lines in gap resolution. I'm talking about large scale commercial production programs. Some of the finer lines are already being manufactured. Early production, smaller scale or niche applications, or maybe high value parts and things like that. Are actually looking at around 100 micron traces for interconnects and about 50 micron traces for transparent, maybe 50, 40 microns for transparent applications. But there are still some challenges with production yields, especially when it comes to larger screen frame sizes and long runs. The in development targets are certainly below 50 microns and ideally even less than 25 microns. And here you can see the images, some examples of our conductive paste and their printability that we've done in the past. You can see some 150 lines and gaps, 100 microns, 75, and then even down to 25. And I'm not quite sure how you're seeing these images, but I see them a little bit rasterized, so hopefully you can see them a bit clearer. Next slide, please. From the manufacturability standpoint, there are many factors that affect the outcome, and things like ink rheology, particle size, type of the substrate or treatment of the substrate, screen parameters like mesh count, emulsion thickness, squeegee shape and hardness, and of course printing process itself, whether it's the printing speed, squeegee pressure, snap off distance, and even operator skill. All of these will affect the outcome. And it really is a whole system that needs to come together to realize a successful high resolution screen printing. Next slide, please. From the ink design perspective, there are multiple things we consider when formulating a paste for high resolution printing or for any application, really. And we need to carefully select individual components as they all contribute to the final properties of the paste. I won't get into too much details on this slide. You can use this as a reference, but I will cover some of these topics in the next slides. Next slide, please. All right, so conductive particles are really the main component, one of the main components, but these are really particles that contribute to conductivity, right? They affect not only conductivity, but also rheology, printability, stability, and things like that. And not to mention the cost, right? As you know, silver is currently a dominant metal of choice for conductive inks, although there are some alternatives on the market, which we will hear about from next speaker. But let's go back to silver. So for the silvers, there are many shapes and sizes available, from large flakes to fine flakes and powders to nanoparticles, and even particle-free options possible in the form of molecular silver inks or precursor silver inks, as we heard from Arnold at NRCC yesterday. And each have their advantages and and disadvantages, but really all are viable options in one way or another. So just for your reference, I'm showing you SEM examples or pictures of silver ink surface prepared with either large flakes or finer flakes, and then also sintered nanosilver. So you can see that the packing density, the sizes are very different, and the surface is looking different, which affects ultimately the performance and suitability for an end application. And as you can imagine, smaller particles are preferred for fine traces, and there's been a lot of new developments from flake suppliers in this area. Next slide, please. Viscosity of the paste is a very common property that we measure and report. We really kind of measure it on a daily basis, multiple times. But in this case, really for high resolution printing, viscosity alone is not a good predictor of how the paste will perform in fine line printing. We're really looking to study or to understand the full rheology profile of the paste. We're looking for higher thixotropy and pseudoplastic behavior, or a paste that will recover fast after printing, that will thin down with the shear, but then recover fast when the shear is removed or when you lift the screens, so that the lines are not really slumping and spreading too much. So the images on the right side actually show you the difference in inks with same viscosity, but one is with fast recovery or higher pseudoplastic behavior versus the right one is with the slower recovery or lower thixotropy. And you can see that slower recovery ink spreads about 50% from the nominal 80 micron design line, while fast recovery ink spread is minimal. We're hitting around 80 micron lines on that. Okay, next slide, please. One of the very important challenges and things we need to consider with high resolution printing is screen stability. And this is especially true for longer press runs and larger screen sizes, or for lines below 50 microns. And again, I'm hoping you can see these pictures a little bit clearer than me on my side, but there's currently a lot of babysitting and handling on press needed to maintain quality and reliability of the sub 50 micron lines throughout the run. And the inks with faster drying solvent or poor resolubility of the resin, they can clog the small openings of the mesh pretty fast. And you can imagine higher count meshes work better for higher sharpness or higher resolution printing. So you can see in this picture on the left side, I'm showing the ink that is drying in the mesh and it's not able to restart clean printing after the idle time. But the right side shows the ink that we optimize with composition and it can retain good printability. Now these images for your reference are a 50 micron metal mesh. All right, next slide, please. Now, you can see this slide is mostly images. I'm really just showcasing some of the work we did with our partners, namely Asada Mesh and WCPC University in Swansea. Left side shows the line topography for 50 micron nominal line printed with different mesh counts. And as you can see, 500 mesh gave the most uniform lines with the close to nominal line with 50 microns, while lower mesh counts showed more spreading and less uniformity in the ink deposit. Now, images on the right show stainless steel 430 mesh with 13 micron wire diameter from Asada Mesh, and the capability with this mesh we were able to achieve down to 25 and 30 micron line widths with low level of spreading. Next slide, please. I'm near the end of my 15 minutes. This slide shows just some examples of our most recent work we did with Asada Mesh, and their stainless steel mesh 520 TPI and 11 micron wire. And this is also with our new generation fine line flake silver ink. So, and as you can see, we were able to demonstrate even sub 25 micron line printability. The finest line are in the region of 15 to 18 micron. And, you know, We continue to work collaboratively with our partners to develop materials and as well as optimize processes. We're looking at the squeegee effects, the printing speed effect. We're looking at multiple substrates and things like that. We're working collaboratively with Kiwo on emulsion and emulsion release coatings that actually help printability of fine lines. So we'll be presenting more data as the year goes. So please make sure to tune in to our LinkedIn website to see the announcement. And in the last slide, please. Actually, I think there was one before this one, Chloe. Yes, there you go. So I'm not going through all of this writing, but I put together some tips for troubleshooting for you for fine line printing. So please make sure to download the presentation after the conference and use it as needed in your development. So it's just little tips and tricks to how to maybe make the process a little bit easier for printing. And very last slide. I would like to thank you all for your attention, and I'd like to also acknowledge our partners, the SADA Mesh, CFAR, WCPC, all of our suppliers and customers that are very supportive in this development. Thank you all for your attention.